In graph theory, a graph is a collection of vertices or dots and edges. That is it. So here's an example of a graph. This has nothing to do with the Cartesian plane, xy coordinates. There are no parent functions, no transformations, nothing from algebra or pre-calculus here. You have a pile of dots, you have a pile of edges, and that's it. There are some rules. The edges have to connect one dot to another dot, right? You can't have an edge just trailing off into space and stopping. We definitely make there be finitely many vertices, so no infinite vertex graphs in this class. There's some other things to know. One is that the vertices don't all have to be connected by edges when you're talking about a graph. So if I have a pile of 6 vertices and 5 different edges, to me, this is a 6 vertex, 5 edge graph. It is a single graph. Now we can talk about it being a 2-piece graph. The formal term is a 2-component graph, but we have to think about this as one indivisible unit. It is one graph. This graph actually illustrates a second point, which is that 2 vertices can have more than one edge connecting them. So these 2 guys in the middle actually have 2 separate edges connecting them. That's fine, we don't care about that. And the third fact is sometimes we have to draw 2 edges that intersect. They look like they intersect, but we don't want to think about there being like a vertex in the middle if it's not literally drawn there. So here's a good example. I'm thinking about a 6 vertex graph, and it's going to have a ton of edges. It's going to have all of these edges. There are actually 9 of them. And it's hard to explain, but this is a special kind of graph that you can't draw without the edges intersecting. You definitely don't want to think about there being any gold-colored vertices in this area right here. It's sort of like if you just had strings that crossed over one another. They were lying on top of one another on a desk, but they weren't actually attached.